we'll review the method of elimination for solving systems of equations. Um, the goal of the elimination method is to end up with what is called an upper triangular system of linear equations. So the system is called upper linear because we have a diagonal in which, or a diagonal system in which the first variable shows up on the first equation, and but not on the second equation. And then the second variable shows up on the second equation, but not on the third equation. So when we have this set up, where essentially we have a 0 here, 0x, and then a 0x and a 0y there, there's no need to put those. Then we see that we have a triangle going on here, and that's why it is called upper triangular system. Now, once we have a system in upper triangular form, then the system is reasonably easy to solve by back substitution. And by the way, the goal is to get a system into another system, into another system, in such a way that the last system becomes an upper triangular system. So we're changing a whole system by another whole system, a step at a time. Yeah. So we're not changing one equation, we're changing the whole system. Now, changing one equation changes the whole system. Anyway, let's figure this out. Once you have this, we can multiply it by 2 on both sides of the equation. So that is going to give us 18. And then when we divide by -3, we end up with -6. So this tells us that z is -6. Yeah, z equals -6. And then if z is -6, well, that is 18. When we put that on the other side of the equation, we have 28 divided by 4. That's going to give us 7. So y equals 7. And then if y is 7 on the first equation, that is going to be 21. 21. And then we're going to add 6 because z is -6, but we're subtracting z. So 21 and 6 is 27. And then that's a positive number. When we put it over on the other side, now I forgot what it was. 21 and 6 is 27. Oh yeah, -27 plus 11 is -16. But then we divide by 2, and that's going to give us -8. So the solution, whoops, I meant to put an x here. X equals -8. So let me just write this more neatly. X equals -8, y equals +7, z equals -6. And that is quickly done once we have the system of equations in upper triangular form. So example 2, how do we achieve the upper triangular form? And there is a method that is extensively used, and it is called the method of elimination, but we have to perform the method of elimination very systematically. Yeah. So let me copy this problem. Z equals 13, 3x minus 2y plus z equals 9, and then 2x plus 3y minus z equals 49. All right, so we have a system of 3 by 3 equations, 3 equations and 3 unknowns, and we want to solve it by the method of elimination. And there is a very, very specific way of doing this. So first we eliminate the x from the second equation. And the way we go about doing that is by multiplying the first equation by 3 and then subtracting that product minus that. So I'm going to do that here on the side. So I'm going to copy down the second equation. So the second equation will be 3x minus 2y plus z equals 9. And then we're going to multiply the first equation times 3. First equation times 3. And that's going to give us 3x plus 3y 3x plus 3y plus 3z equals 39. And we're going to subtract the 2. Okay. This number that we're multiplying by is called the multiplier. And this guy is called the pivot of this algorithm, this method we're using. So then we subtract. That's going to cause the x's to go away. Negative 2y minus 3y is negative 5y. Z minus 3z is negative 2z equals 9 minus 39 is negative 30. Let me double check. 2 minus 3, rather 1 minus 3. Yep, so everything turns out to be negative. Okay, so now this system becomes, well, is changed into a new system, x plus y plus z equals 13, negative 5y minus 2z equals negative 30. Oh, there's one other thing I missed to do. We need to also eliminate the x from the third equation. Barnacles, where do I do that? There's not a lot of room on this page. Let me do that down here. So take the 2x, take the third equation as is. So this is going to be the third equation, and it is going to be 2x plus 3y, 2x plus 3y minus z equals 49. And we want to multiply the first equation by 2, the same pivot value. So the first equation, we're going to multiply it by 2. So we can end up with 2x. See, the goal is to end up with the same, with matching coefficients for the variable we are attempting to eliminate. And then 2y, 2z plus 2y plus 2z equals 26. And then again, we subtract. So no x, 3 minus 2 is a y, negative z minus 2 is negative 3z, and then 9 minus 6 is 3, 4 minus 2 is 2. Okay, so now we have this system, the new system of equations, which is x plus y plus z equals 13, negative 5y minus 2z equals negative 30, and then y minus 3z equals 23. Okay, so we went from this system of equations to this new system of equations, which is more upper triangular. It's not totally upper triangular because when we have a 3 by 3 system, we should have 0 here, which we already have, 0 there. So we have to multiply this guy by something that causes those two, well, this coefficient to, well, let me say it again. We have to multiply this equation by a number so that after multiplying by that number, we get a coefficient matching this coefficient, which is 1. Okay, so now we move on to that step. All right. So take equation 3 again, which is going to be y minus 3z equals 23, and then multiply that by something that causes the coefficient after the product happens to be 1. So we take the second equation and multiply by -1/5. So times 1/5. All right, -1/5. So -5y times -1/5 y. -2 times -1/5, that is positive 2/5. -30 times -1/5, positive 6. And then we subtract. Y minus y, no y, that is the goal. -3z minus 2/5 of z. Well, that is 15/5. 3 is 15/5. And then we're going to subtract 2 of those 15/5. So we're going to end up with 13/5 of z equals, and 23 minus 6 is 17. Let me double check something real quick here. A negative, we're subtract with a negative, so we end up with positive 1. And then 2/5, that is correct. And then 1/5 of 30 is 6. Positive. And we're subtracting this minus this. Oh, here, I made a mistake in this step. This is -15, -15 fifths, but then we're going to subtract 2/5. So we end up with -17/5. There we go. -17. Whoops, I already had a 1 in there. It's not 117. Oh, there we go. All right, so now our new system of equations becomes x plus y plus z equals 13, -5y minus 2z equals -30. And then that's the one equation that got eliminated. And the new equation is -17/5 -17/5 equals 17. Oh, I'm missing the z. There we go. Okay, so now we got an upper triangular system of equations that is equivalent to the original systems of equations. So if we are asking for the upper triangular system of equations, there we have it, equivalent to that one. And it requires us to multiply once and subtract, and to multiply twice and subtract, and to multiply 3 times and subtract. So it required 3 operations of rows. These are the rows to end up with this answer. So this is the upper triangular system. Upper triangular system. So if we were asking to find the upper triangular system, stop here. You don't want to continue any further. Now, once we have this, then it's easier to find the solutions. All we have to do is back substitution, as in example 1. You know, it's very easy to say, well, you can divide by 17, and the 17s go away, and multiply by -1, rather by -5. So directly we can tell z will be 5. Okay, so if z is 5, well, that is -10. When we move that over, that is, we're going to end up with negative 20. And if we divide by negative 5, we end up with positive 4. So y will be 4. And then if we know that is 4 and that is 5, 4 and 5 is 9. So what number plus 9 gives us 13? Is it 5 again? Let me check. 5 and 4 is 9. No, I'm too short. I'm going too far. So again, 9. Oh, I cannot do this. So 4 and 5. It looks like it's 4. Again. Let me double check this. So negative 20, and negative 10. Yep. That's negative 30. And of course, that is, because if z is 5, oh, there's a problem here. Z is negative 5. No wonder why. Yeah, I missed the negative. Yeah, let's erase this very quickly. Yeah. Yeah, this is negative 5. Yeah, because of the negative. So that is positive 10 when we multiply. Negative 40. So y has to be 8. Yeah, that makes more sense. Okay. And then 8 and 5 and negative 5 makes a 3. 8 and negative 5 makes 3. So x has to be 10. Boy. That's what happens when I try to do too much on my head. 10. Now that makes more sense. Let's double check to be sure that actually solves the original system. So the 3 together, 10, 18, and negative 5, sure enough, that works. 30 minus 16 is 14. 14 minus 5 is 9. That works. 20 and 24 is 44. And 5 is 49. Sure enough. So yes, that is the solution to the system of equations. Yeah. By the way, going back to vectors, what this tells us is that there's a linear combination. Okay, so this system can be rewritten as a number x times the vector 1, 3, 2, 1, 3, 2. So 10 of those plus 8 of the vector 1, negative 2, 3, 1, negative 2, 3, minus 5 of 1, 1, negative 1. That is equal to the vector 13, 9, 49. 13, 9, 49. Yeah, so solving the system of equations is equivalent to finding the linear combination of those 3 vectors that yield this vector. Yeah. Now, it turns out that when we look at this system of equations, we have 3 different vectors. Yeah, that is interesting. So 10 of 100, 100, plus 8 of 1, negative 50, 1, negative 50, minus 5 of 1, negative 2, and this weird fraction, negative 17 over 5, will equal 13, negative 30, 17. Yes. So notice that we have the same linear combination of different vectors, though. Those are not the same vectors. And we don't have the same resulting vector either. We have different vectors. Now, we could do even better. We can make this unit vectors. We can keep eliminating and get rid of those. Just as we eliminated down this way, we can eliminate, once we have this, we can use this as the pivot and then eliminate those two. All right, so that is how we proceed with the method of elimination. There are a couple complications. Let's look at example 3. Okay, so we will have 2x plus 3y plus z equals 43. 2x plus 3y plus 2z equals 49. X minus y plus z equals 7. Okay, and let's proceed the same way. We're gonna find a multiplier of this two to match this two. But that is pretty straightforward. That's gonna be 1. Yeah, so there's the system of equations. And after the first transformation, I mean, typically we write down the second equation and then subtract the multiplier times this equation. And actually, but this is going to be so straightforward. I'm just going to do it without actually showing you what is going on, because those already match. So we can do the subtraction as is. So 2x plus 3y plus z equals 43. That equation does not change. And now we're going to subtract 2x minus 2x, no x. 3y minus 3y, no y. 2z minus z, a single z. And 49 minus 43, 6. Okay. Now for the third equation, we have to do some work because the coefficients don't match immediately. Okay, so we're gonna put this last part on hold, and we're gonna do the computation down here. So the third equation 3, is x minus y plus z equals 7. I'm just copying it down, and we're gonna take the first equation and multiply it by a half. And that will cause this 2 to become a 1, making it a matching coefficient. So 2 times a half is 1x. 3 times a half is 3 halves y. Z times a half plus half z. And 43 times a half is 43 halves. Okay. X minus x, no x, that was the whole point. Y, 1y minus 3 halves y, that is negative half y. 1z minus half z. Wait a minute, I almost fell for this again. X minus x is no x. Negative y minus 3 halves. This is already negative. So when we subtract, we actually end up with 5 halves, not 1 half. Yeah, so this is going to be 5. Again, negative 1, and we're subtracting 3 halves. Well, negative 1 is already 2 halves, or negative 2 halves, minus 3 halves, that is the negative 5 halves. All right, so 1 minus a half, that is still a half. And these are 14 minus 43. I'm going to do it this way, negative 43 plus 14, because we're going to subtract. So 13 minus 4 is 9. We borrow 1, so 3 minus 1 is 2. Okay, so that's going to give us negative 29 halves. Boy. negative 5/2 y plus a half z equals negative 29/2. All right, so there is our second system of equations. We have converted this system of equations into this system of equations. This was the pivot element, and the first multiplier was 1, and the second multiplier is 1/2. But now we have an issue. We want to create an upper triangular matrix, and so we want to get this to be 0. But in order to get this to be 0, we need that one so we can eliminate, but that one does not exist. So we have a problem. This method failed right now because we cannot proceed as is, because in order to eliminate this guy, we need a y here. And by the way, we cannot use this one, because if we try to use this one, it will work. We will eliminate this guy, but that is going to create another x to show up in here. So we really want to go down the triangle. And so we have a problem. The problem is not too difficult to solve. The way we solve this problem of not having an element here to eliminate the next one down is to simply swap the two equations. We're going to swap the two equations, and now we're going to have a new system. All right, so 2x plus 3y plus z equals 43. This one is going to occur second, opposite of 5/2 y plus a half z equals opposite of 29/2, and then z equals 6 last. All right, so we are finished. So it only took, let's see, 3 steps to get to upper triangular form. We eliminated the x here, eliminated the x there, that's 2 steps. And then we swap, and voila, we are all set with the upper triangular. So if we are asking for the upper triangular form, there it is. If we want to solve the system of equations, then we go farther and we say, okay, if z is 6, so that's already established, then that is 3. 3. Because 6 divided by 2 is 3. Or the other way to put it is 6/2. And we're going to move that to the other side of the equation. That's probably going to be easier. 6/2 on the other side. That's going to make negative 35/2. But then we can multiply by the reciprocal of the 5/2. Negative 35/2. I'm trying to remember what it is. So that means that y has to be 7. And if y is 7 and z is 6, let's say 21 and 6 is 27. 21 and 6 is 27. 43 minus 27, 13 minus 7 is 6. 3 minus 2 is 1. Oh, so 2x is 16, and that means that x has to be 8. So there is the upper triangular form of the system of equations, and then there is the solution. Okay. And difficulty with this example is that we had to do a swap of rows of equations. Otherwise, we cannot proceed. The problem is the way of solving this gets jammed because there's no equation to eliminate this variable. And that happens. So we have to do a swap. Example 4 is going to be actually simpler. 2x plus 3y plus z equals 8. 2x plus 3y plus z equals 7. And if we want to eliminate, we can simply do the subtraction, this minus that, because the coefficients already match. So if we want to eliminate the x, we end up with, let me write down the first row as is, and then the second row will be the subtracting that row minus the first row because the coefficients already match. So 2 minus 2, no x. 3 minus 3, no y. Z minus z, no z. So we end up with 0 equals 7 minus 8, negative 1. Okay, so this system is equivalent to this system, but this system has a contradiction. This is 0 is not equal to negative 1. That doesn't mean we cannot write it down. It just means that it is a false statement. So this is a contradiction, which means that we cannot come up with this vector with those vectors. Yeah. So there's no way. There is no way, okay, to combine, let's see, 2, 2, 3, 3, and 1, 1 to obtain 8, 7, which makes sense. Think about that. Actually, this is redundant because twice this gives us that. This is redundant because 3 times this one gives us that. So those two can be eliminated. All we need is this one. So 1, 1 is sufficient to generate those two. So that is sufficient for anything for any linear combination of the 3. But there's no way we can get 8, 7 using only this vector. We cannot get 8, 7. Yeah. Geometrically, what is going on is that 1, 1 goes diagonally, and 8, 7 is off the main diagonal. I'm exaggerating a little bit here. So it doesn't matter how many vectors of those you try to add, we're never going to be able to veer off and get to 8, 7. Yeah. So that is what's going on. And if we use 2, 2, well, that is just that and that twice as much. So that's not going to happen. 3, 3, same. And even if we have negatives, we're never going to be able to veer off to obtain this. So there's no solution for this system of equations. Were we able to write it in upper triangular form? Well, I don't know if that even makes sense because this is not even a square system. We don't have the same number of rows as variables. But still, even if we were able to, we have a contradiction. And so the system has no solutions whatsoever. No solution. Can't happen. Example 5 is different. Say you have 2x plus 3y plus z equals 8, 4x plus 6y plus 3z equals 10, 6x plus 9y, predictably, because we got 2, 4, 6, 3, 6, 9, plus 4z equals 18. Okay, and let's go ahead and change this into a system of equations that is upper triangular. Okay, so this is the first pivot. and we're going to keep that equation as is, plus z equals 8. I'm going to try to do the next operation in our head. You know, all we have to do is multiply by 2, and then we subtract. So remember, we're going to multiply this by 2, and we're going to have 4x's, 6y's, 2z's, and 16. 4, 6, 2, 16, when we multiply this by 2. So that is the first multiplier, and then we subtract. 4 minus 4, no x. 6 minus 6, no y. 3 minus 2, remember, we're multiplying this by 2. So 3 minus 2 is 1, z. And 10 minus 16, remember, we're multiplying this by 2. So 10 minus 16 is negative 6. Then we do the same thing here. 6. Now, but the multiplier is going to be 3. We're going to multiply this guy by 3 so that the coefficients of the x match. 6 minus 6, no x. 9 minus 9, because we're multiplying this by 3, no y. 4 minus 3, remember, we're multiplying this by 3. So we end up with z. 4 minus 3, and then 18 minus 24, negative 6. Okay, so it's clear that z is negative 6. Oh, well, wait, let me back up a little bit. We have an upper triangular system. So this is upper triangular because we have 0, 0, 0. So that is upper triangular. Never mind that this is also 0. Okay. If we were to solve the system, okay, it would be clear that z is negative 6. That's clear. But what about x and y? We don't have a way to get y by itself, and or x for that matter. So this is a problem. If z is negative 6, let's think about this. If z is negative 6 in the first equation, that means that if we add 6 to both sides of the equation, we end up with 14. So what we can say is that 2x plus 3y has to be 14. But there are many possibilities to do this. If y is 3, for instance, yeah, so 3 for y and 2 for x will do. So 2, 3 is a solution. 4 plus, yep. No, that is 13. That won't work. I need a 5, so 2.5. Whoops. So 2.5 and 3. There we go. So 9 and 5. There we go. That is one solution. But y could be, I don't know, 4. So that is a 3. That would be 12. So 1, 4, that's an easier number. So 1, 4 is another solution to that. So actually the solution has to include the z. So we have really, including the z, 2.5 or 5 halves, 3, negative 6. That's one solution. Another solution is 1, 4, negative 6, and so forth. There's many solutions. For instance, we can have 0 for y, and that will cause x to be 7. So 7, 0, negative 6, another solution. Well, if we want to give all the solutions, we have to use a parameter. You know, just fix x to be anything. So x could be anything, and then you can solve for y. So all solutions would have to be, let's see, well, there's a couple different ways to do it. We can use the parameter, the x as the parameter. So x is free to be whatever it wants to be, But once x is fixed, then y has to be 14 minus 2x over 3. 14 minus 2x over 3. And then z is stuck at negative 6. So there is one way to represent the solution. You put x there, and that is our parameter. And then the second coordinate has to depend on x. Or we can let y be the parameter, negative 6 is stuck, and then we can solve the equation for x, this equation. So 14 minus 3y, 14 minus 3y over 2 will do. So that is another way to solve or to represent all the solutions. I'm trying to think if there's another possibility. There's a couple different possibilities, but we're going to keep it simple that way. Yeah. And this is the first introduction to the elimination method. Now, I did not show any 2x2 system of equations, but I'm assuming that if we can do 3x3 systems of equations, 2x2 systems are going to be simpler. Okay, we're going to stop the video here.